So far we have learned how to deal with a couple different types of differential equations. We have learned to actually solve what are called separable differential equations, and those are ODEs that look something of the form where we can basically separate our functions of y and our functions of x in this form. It's really nice. You just take the antiderivative of both sides. Life is good. Then we also learned about the integrating factor method. And so this particular method requires that our differential equation be first order, so do all of these, but that it also is linear. And so that's if we have a differential equation of the given form, y prime plus p of x times y is equal to q of x, and there's a method for that. So this is first order, and linear is the requirement. It's pretty much the only requirement. And then for separable, I mean, the quality for separable is that you have to be able to separate it. But this works on, this could be a nonlinear differential equation, could be homogeneous, non-homogeneous, things like that. But again, the important thing is that we can separate it. And now we're on to this thing called exact ODEs. And this is another classification of differential equations that's a little weird because it requires the most sort of background theory to make work, right? Separable, just requires, you remember Calc 2 essentially, that you were like, oh yeah, I can integrate stuff. The integrating factor method just requires that you really know how to do Calc 1 and Calc 2, which is, that you know how to take the derivative with the product rule, and then you know how to take an integral. But exact ODEs require some knowledge from Calculus 3. And so what we need to remember is this concept, which we call the total differential from Calculus 3. And the total differential presents itself in the following formula. It says it's equal to the partial of z with respect to x times dx plus the partial of z with respect to y times dy. Now, the best intuition I can give for this would be to very quickly return to Calculus 1. And remember that, in Calculus 1, we learned that this thing called dy dx is equal to f prime of x. We said this is the slope of a function. And the idea is that if I know the slope, let's say, dy dx is equal to 3, I could, if I wanted to, I could rewrite this equation as dy is equal to 3 dx. And what this means, remember that this is my slope. This is my slope, or my rate of change. And it tells me that if you give me some little change in x, I can tell you what little change in y you would be expecting at that point. So for instance, if we know that our change in x is 1, right? If this is 1, we would expect the change in y to be 3 because that's how slope works, right? That's rise over run. We expect, according to this little formula, that our slope is 3. And similarly, if I gave you, for instance, that our change in x is 4, we would expect our change in y to be 12, to be 3 times larger, again, because of the fact we know about this slope. Now the thing is with 2D calculus, where we have one input variable and one output variable, we only have one input variable, right? We only have to worry about a change in x affecting the change in y. But in 3D calculus, we have these 3D equations kind of manifest themselves as surfaces. And when we're talking about making a change, going to another point, in 2D, this is just, you have 2 points, you go here and you can figure out the slope. But if I want to figure out kind of my change in z, right, headed towards this other point, meaning that if I were to kind of navigate towards that point, what would my overall dz be, my change in the z value? Well, my function itself, this surface depends on 2 variables, which means that I'm going to get, if I were to, and I'll draw it down here, if I were to go for a walk in the x direction, some dx, there's going to be some change in z that is a direct result of my going in the x direction, but there's also going to be, if I were to say go for a walk in the y direction and there's a change in y, there's also going to be some change in z that happens as a result of going in the y direction. And so the two of those things combine to give you this thing called dz. Okay, this total differential, this total change in z. You figure out what is the rate of change in the z direction courtesy of x, and then you scale it by however much you change in the x direction, very much so like how we did down here. And then you also want to include how much you change in the y direction, or the rate at which you change in the y direction scaled by your change in y. Now, all of that is just simply background theory to kind of remind ourselves about this thing called the total differential.